So now we understand that the derivative is the slope of the tangent line of the function. But what about the second derivative? What is that? This is climb time, and today we're going to look at graphs of f, f prime, and f prime prime. We're also going to look at something called concavity. So we have a function f here. It's a quadratic, a parabola, and the derivative of that I've given to you ahead of time is actually a line. And what this graph is a graph of all the slopes of all the tangent lines of f. And then we have another derivative, a derivative of the derivative, which we call the second derivative. You see we have two slashes there. If one slash, one apostrophe is one derivative, two apostrophes is two derivatives. So f prime prime is the derivative of the function f. So now let's take a look at how this makes sense and what's going on here. All right, so if I take a look at the slope of the tangent line, let's draw a little tangent here. I have a tangent right there. And what you see is the slope is 0. And so the slope here is actually the y value here. So where the slope is 0 there, the y value here is 0. And so if I go to the right of the y-axis, you can see my slope is going to be positive, reading left to right and going uphill. And so the slope here is the y value here. And so you can see the y values here are positive to the right of 0. So here, the y value is 0. Here, the slope is 0. Here, the y value is positive. Here, the slopes are positive. And here, the slope is negative. Here, the y value is negative. So the slopes of this correspond to the y values of this. So I'm going to draw a little arrow to try to indicate that in some way here. So slopes, slopes turn into y values. And that's what's happening from here to here. So these slopes become these y values. So in the same way, we can do the same thing with this graph down here. And we can say these slopes become these y values. So the same thing happens here. And the reason why the same thing happens here is because f prime prime is the derivative of f prime. So therefore, all the y values here represent all the slopes here. And so the slopes of the tangent line here are all the same, and they're positive. So these positive slopes turn into positive y values here. So here's the key takeaway. As you go from f to the derivative of f, the slopes become the y values. And if we take another derivative, then the slopes of this graph become the y values of that graph. And that's how f prime, and f prime prime are related to each other. Now, I want to point out something else. And what I want to point out here is if you look at the slopes, why this f produces this f prime graph. We talked about 0, we talked about positive, we talked about negative, but we can do better than that. We can talk about more than just that. What we notice is that the slopes here is negative, and then it's less negative and less negative until it's eventually 0, and then it's positive and becomes more positive and more positive, and it will continue to get bigger as we go along. So this one is going to be even steeper than that one is. This one is going to be, yes, steeper, but more negative. So more negative means smaller. So this slope is smaller than this slope, which is smaller than this slope, which is smaller than this slope, which is 0, which is smaller than this slope, which is positive, which is smaller than this slope, which is bigger and steeper and bigger and steeper and bigger and steeper. So if something has a big magnitude, but it's negative, that's considered a small number. If something has a big magnitude and it's positive, that's a big number. So the slopes are continuously getting bigger. They're continuously increasing. So I'm going to write that down. Slopes are increasing. Okay, and that is true for this graph here. The slopes are increasing. So I'm going to draw an arrow to that so we can see that slopes are increasing. So the slopes on this one are always increasing, which means the y values of this guy have to be continuously increasing. So the y values on this guy are increasing. So I've got enough room to write that. Okay, so the slopes of that one is continuously increasing because the slopes here are continually increasing. They're getting bigger and bigger and bigger and bigger as we go around. That means the y values in this one are continuously increasing. So they're starting with a big negative number and we're eventually going to zero. Then we're going to a big positive number. So y values are continuously increasing. And so this guy's y values is based on slope on that. And the slope of this is constant but positive. I'm sorry, constant positive y value because it's the slope of that one. So this one has constant positive y values. So again, the y values of this graph is coming from the slope of that graph. And I smeared that and I don't like that, so I'm going to rewrite that again. Okay, so because the slope is constant here, the y values are constant here. And because the y values are continuously getting bigger here, that means that our change is positive. And that's why this is positive. This is positive because our change is positive. So that's how you get from F to F prime to F prime prime. At this point in time, you may not know how I came up with this graph and this graph, but there's some properties that should make sense. And one property is that when this has a zero slope, this will have a zero y value. When these slopes are positive, these y values should be positive. When these slopes are negative, these y values should be negative. And if the slopes are always getting bigger, they're continuously increasing, then this function should be continuously increasing. It doesn't necessarily have to be a straight line like this, but it does have to be continuously increasing. Now, we can do the same, follow the same method from this graph to this graph. This one never has a zero slope, so this one should never have a zero y value. This one never has a negative slope, so this should never have a negative y value. This only has positive slopes, so this should only have positive y values. And that's how you get from one graph to the next to the next. All right, let's look at the same thing, but everything's flipped upside down now. So let's take a look at the slopes. So if you look at the slopes, actually I'll use orange for this one. So if you look at the slopes, you can see right here, the slope is zero, slope of the tangent line. So therefore, the slope of that guy is the y value of this guy. So since the slope is zero there, the y value of this guy is zero because this guy's y values are this guy's slopes. And right here, the slopes are positive because reading left to right, they're going uphill. So therefore, this guy's y values are positive. And over here, this guy's y slopes are negative. They're going downhill. And so this guy's y values are negative. So zero y value, zero slope. Positive slope of the tangent line, positive y values. These are positive y values. Negative slopes of the tangent line, negative y values. So that's how we get from here to here. In addition, the slopes here are constantly decreasing. So the slopes are decreasing. Okay, and I know that. So the slopes of the tangent line are decreasing. I know that because I'm going to start with a large magnitude positive slope, and eventually it'll get smaller and smaller and smaller and smaller and smaller and smaller until eventually it's zero. So I go from a large positive number to zero. That's getting smaller. And then from zero, I get to a small magnitude negative, then a larger magnitude negative, and a larger magnitude negative. And so I'm getting more and more negative. Going downhill is a negative slope. So I'm going from a very large positive number to zero. From zero, I'm getting to more and more negative numbers, bigger and bigger magnitude negative. That means the slopes are constantly decreasing, which means on this graph, what we would expect, and that's what we see, is that the y values are constantly decreasing. Y values are decreasing. So the takeaway here is that the y values of one is the slopes of the other. Since f prime, oh, that looks like two primes, doesn't it? That should just be one prime. F prime. And then this one down here should be f prime prime. I think I did have two primes there, but it should be f prime prime. All right, so y values of this represent the slopes of that. The y values of this represent the slope of that. And so because the slopes are constantly decreasing, the y values are constantly decreasing. So again, while we may not know exactly what the graph looks like at this point, there are some properties we should know. And we should know where the y value should be 0 on the first derivative graph, because we know where the slope is 0. So if we know f, or we have a graph of f, we can see where the slope is 0, and that's where the y value of this should be 0. We can also see where the y values are, where the slopes are negative, and that's where the y value should be negative here. We can also see where the slopes are positive, and that's where the y values should be positive there. We could also see that the slopes are constantly getting smaller. So therefore, the y values here should constantly get smaller. We may not know just by looking at the graph of f that this is a straight line like that, but we would know that it's constantly decreasing, and we would know where it's positive, where it's 0, and where it's negative. All right, now let's look at f prime prime. So with f prime prime, we can see because the y values are decreasing on this one, that means the slopes are constantly negative. So slopes on this guy are constantly negative. So therefore, the y values of this guy have to be constantly negative. So y values on this one are all negative. And the reason why, again, is because the y values of this are the slopes of that. And the slopes of these are all negative, so therefore the y values of these are all negative. There's no place on this one where the slope of the tangent line is 0. Therefore, there's no place here where the y value would be 0. There's no place on this one where the slope of the tangent line is positive. No place where it's going uphill. So therefore, there's no place here where the y value would be positive. So therefore, the y values have to all be negative. That means it has to be all below the x-axis. And this is one option here. All right, so that's how f, f prime, and f prime prime are related to each other. And they have to do with understanding slopes. So f prime, so y values are the slopes of f. F prime prime's y values are the slope of f prime. Now, I want to talk about how f prime prime is related to f. And the way f prime prime is related to f is like this. I've given you two examples. One example is when f looks like this, looks like a smiley face. Okay, there's a word for that. It's called concave up. And whenever f is like a smiley face like that, or concave up, then the second derivative will always be positive. Okay, so just like our example here, we just showed that if this looks like this, kind of like a quadratic or parabola, f prime prime has to be positive. All the y values have to be positive here because of the way f prime looks. So this is always going to be true. So when f is concave up, f prime prime will always be greater than 0. So again, we have a word for that. It's called concave up. So I will put this down below, maybe a different color for that one. So this one is concave up. And then, as you can imagine, we can go the other way. So when f is like a frowny face, it's an upside down problem, then f prime prime is less than 0. And we call that concave down, as you can imagine. So this is concave down. We have concave up and we have concave down. So you can think of it like this. When the function is smiling, the second derivative is positive. Maybe it makes the second derivative happy. When the original function is frowning, the second derivative is negative. Maybe that makes the second derivative unhappy. But we call this concave up, we call this concave down, and we know that the second derivative will always be positive when it's concave up. Second derivative will always be negative when it's concave down. So now you might be asking a question, and maybe you should be asking a question, what happens when the second derivative is 0? Okay, and that's a very good question if that's what you're asking. So let's put that in. What happens when the second derivative is 0? So when f prime prime is equal to 0, then it might be the case that it switches concavity. then F might switch concavity. It's not a guarantee, but it's a possibility. So it might go from concave up to concave down, or concave down to concave up. And what that looks like, running out of space, so I'll have to draw it over here somewhere. What that would look like if something is going from concave down to concave up, looks something like this. So here's concave down, and here's concave up. So this one, the slopes are always in. So for this particular one, it's actually, yes, concave down. So the slopes are constantly decreasing. And on this one, the slopes are constantly increasing. So that would be a switch in concavity. And so if that happens, we have a name for that. We call that an inflection point. If that does in fact happen, we call that an inflection point. You might have heard that word out in the popular media, inflection point. That's where something is switching, something significant is switching. And so in this case, what's switching is concave down and concave up. Concave down, and this is concave up. So if you happen to switch between concave down and concave up, that would be where the second derivative is equal to 0, and that's called an inflection point. So there's a little introduction to concavity. And so basically that can help us understand what the second derivative is doing just by looking to see if the original function is concave up or concave down. If it switches between concave down, concave up, second derivative would be 0, and that's an inflection point. But if you get a case where it's always concave up, the second derivative will always be positive. Get a situation where the function is always concave down, then the second derivative will always be negative. So hopefully that's helpful in understanding how f prime, and f prime prime are related.